In our next section, we will see things start to come together. And what I mean by that is we need to learn to write balanced equations for chemical reactions. So up to this point, we've really just looked at what the chemical equation that represents the reaction looks like. But here we need to go one step further. And in order to do that, we need to understand what the law of conservation of mass means. So every time a chemical equation is written correctly, we are observing the law of conservation of mass. And it's just what it sounds like. Mass is neither created nor destroyed, so it has to be conserved. Whatever mass I started with at the beginning of a reaction is there at the end. And we know, practically speaking, this doesn't always work because we're doing some of these reactions in an open environment, it's not contained. So we end up, especially with gas forming reactions, losing some of our product. But in a perfect world, we would have a completely enclosed system. And what we would see is that all mass, even that of gas that's released through the course of the reaction, will be conserved. How do we make sure that mass is conserved throughout the course of a reaction? We have to make sure we're writing the equation correctly. So we've already done this part. We've read the description of the reaction. This is what we did in the last section. We write the correct equation, including states. So we've already done the first two steps. The next thing we have to do is to add a coefficient to balance. We cannot change the identity of the compound. So what I mean by that is if we have something that looks like this, H2O, H2O has to stay H2O. If I'm trying to say now that I have 4 hydrogen instead of 2 hydrogen, I cannot do this. This is not H2O anymore. This is H4O. It is not the same thing. So that is what I mean by changing the identity. I can, however, add coefficients. And if you've heard the term coefficient before, if I'm looking at the term 2x, that 2, that number in front that multiplies, is the coefficient. So if I'm looking at H2O and I want to make sure that I have 4 hydrogen, I need to put a 2 in front. The only place I can add numbers to change the amount of atoms that appear on each side of a reaction is to put a coefficient in front of that compound. What we have to remember is that if I wanted now 4 hydrogen from this side of the reaction, this doesn't only change the number of hydrogen, it also changes the number of oxygen. So whereas before I had 2 hydrogen and 1 oxygen, that multiplies everything in that formula by 2. So now I have 4 hydrogen and 2 oxygen. So we have to remember to distribute that coefficient throughout the entire formula. We have to make sure that the coefficients are smallest possible integers. So what I mean by that is if I have something like H2 plus O2 yields H2O, and I, for example, put a 2 here and a 2 here, this would be how I would show the reaction balanced correctly. However, balancing can be tricky. And a lot of times what you will do is you will go back and forth and back and forth and back and forth and try to get the correct answer, and you'll kind of overshoot the correct answer. It's a lot of guess and check. So sometimes what I see is something that looks like this. So these are not the smallest integer coefficients. These coefficients, the 4, the 2, and the 4, can be further reduced. So all you have to do is to make sure that those appear in the same ratio in lowest forms. And that would be the same thing as writing 2H2 plus 1O2 yields 2H2O. You do not have to include a coefficient if it's a 1. Just like writing formulas, as long as I write the formula there in the first place, the coefficient of 1 is implied. For the first one, liquid ethanol reacts with oxygen to form gaseous carbon dioxide and water. Pause your video, take a minute, and try to get the correct equation based on this reaction statement, and then we'll come back together and talk about how to balance this equation. So they already told us we have C2H5OH. They're telling us that it's liquid. This is a pure liquid. This is not something dissolved in water. They're telling us it reacts with oxygen. We know oxygen is diatomic. You always want to leave a little bit of space right before whatever compound you're writing, just in case you end up needing to write a coefficient in that spot. To form gaseous carbon dioxide, which is CO2. We know at this point that oxygen is a gas. We know CO2 is a gas. And water. And if it's not specified the state on water, you're to put liquid. The way to approach this from a balancing perspective is to first make sure that your reaction is correct and that you have all of the same elements on each side. So what I would do is draw a line down the middle just to separate the left from the right, or the reactants from the products. And I would list the elements that appear on each side. So we can see on the left, we have carbon, we have hydrogen, and we have oxygen. And on the right, again, we have carbon, oxygen, and hydrogen. So we have the same elements that appear on both sides. We know then that our formulas are probably correct. If you end up with one element on one side that's not on the other, then you have to go back and check your formulas because you've probably missed something. Now what we want to do is count up the number of elements that appear on each side. So we can see, and hopefully you remember from the warm-up, how to tabulate elements based on their formula. But we can see on the left, we have 2 carbon. On the right, we have just 1. On the left, we have 6 total hydrogen. We've got 5 here and 1 here. And on the right, we have 2. On the left, we now have 3 oxygen, and we have to count up the oxygen that appear in both of the formulas. So we have 1 here and 2 here for a total of 3. On the right, we also have a total of 3. So we're going to write 3 right here. Is this reaction balanced? No, it's not. Even though we have the same number of oxygen on both sides, the number of carbon and hydrogen are different. A reaction is not, or an equation rather, is not completely balanced until all of the numbers are exactly the same on both sides. So we can start really in any place. We can't start with oxygen because we're already balanced there. But what will start to happen is we'll go back and forth, and as we change the number of carbon or hydrogen, we could end up changing the number of oxygen as well. So let's just start at the top and work our way down. If we're looking at carbon on the left, I have 2, and I have 1 carbon on the right. You have to think of coefficients as multipliers. So a lot of people will look at this and say, oh, well, I have 1 on the right. I only need 1 more, so I'm going to put a 1 in the front. That is not the correct thinking here. You need to put whatever will multiply that element to get the right number in front. So since I already have 1, I'm multiplying it by 2. This makes my total number of carbon on the right side equal to 2. This also changes the number of oxygen in this formula. So you can see I started with 2, but I put a 2 in front, which means whereas before I had a carbon, an oxygen, and an oxygen, now I have 2 of those whole molecules. So I have 2 carbon, oxygen, oxygen molecules, which means now not only do I have 2 carbon, but the number of oxygen has changed now from 3 to 5. I have the 2 from the CO2 and the 1 additional from the H2O. Now, we can either look at the oxygen. I would not recommend this though, because your oxygen exists in 2 locations on the left side. It exists here and here. So rather than look at the oxygen, what I would do is look at the hydrogen next. We have a total of 6 on the left. We want a total of 6 on the right. I already have 2 on the right. So what times 2 is going to give me a total of 6 hydrogen? If I put a 3 in front, then that means I now have a total of 6 hydrogen. But I've changed the number of oxygen atoms on this side now. So now I have 3 from the H2O, and I have an additional 4 from the CO2. So this gives me a total number of oxygen of 7 on the right side. Going back to the left, I'm still not balanced because you can see now I've messed up the number of oxygen in this balanced equation, not yet balanced equation. So I need to get a total of 7. I can see that since I already have 2 here, I would need to put a 5 in front of the ethanol. However, I don't want to do that because if I put a 5 in front of ethanol, then I mess up all of those other numbers. So instead of looking at it that way, you want to look at it as what can I put in front of O2? We have to remember that one of the oxygen on the left side comes from ethanol right here. So that's not going to count as one that I'm going to manipulate. So I only need an additional 6 more. That 6 more, those 6 more can come from the O2. If I put a 3 in front, 3 times 2 is 6, plus the 1 from the ethanol gives me a total of 7. Now you can see 2 carbon on the left, 2 on the right, 6 hydrogen on the left, 6 on the right, 7 oxygen on the left, 7 oxygen on the right. This is balanced. This reaction should look familiar. We did it with the last set of notes that we looked at. So you can refer back to that to write it down or pause your video and try again to come up with the correct equation. But we know that we have solid potassium. It's going to react with liquid water, and that's going to form gaseous hydrogen. We know hydrogen is diatomic, and potassium hydroxide, and we know potassium hydroxide is KOH. They tell us it dissolves in water, so we know that that is an aqueous compound. So we have our equation, correct with formulas, reactants and products, states. Now we draw our line and we list the elements that appear on both sides. Potassium, oxygen, and hydrogen appear on both sides. So we know we have, or we probably have the correct formulas. Our next step is to list how many of each appear on each side. So we can see that we have 1 potassium on the left, we have 1 on the right. For oxygen, we have 1 on the left, we have 1 on the right. For hydrogen, 2 on the left, and almost but not quite, we have 3 on the right. The only place we can start here is hydrogen. We need 1 more hydrogen on the left side, but hydrogen only comes in 2s on the left side. So 1 more hydrogen isn't going to work. Instead, we can put a coefficient of a 2 in front. So after we put the 2 in front, we need to recognize that the hydrogen are now changed from 2 to 4. And the number of oxygen have now changed from 1 to 2. Now we can see on the right, potassium is still balanced. We haven't touched that yet, but we do need 1 more oxygen and 1 more hydrogen. And we don't want to touch this first H2 because it doesn't have the oxygen in it anyway. But if we look at the other compound, the potassium hydroxide, the KOH, we can see that this has both an oxygen and a hydrogen in it. And since we need 1 of each, if we put a 2 in front, that gives us a total of 2 oxygen and a total of 4 hydrogen, 2 from the potassium hydroxide and 2 from the H2. We're almost there, but what we also have to recognize is that the potassium also changed from 1 to 2. So now the only thing we have left to balance is the potassium on the left side of the equation, which means since we need a total of 2, we're going to put a 2 in front, and this changes potassium from 1 to 2. And we can see that we have the same number of each element on each side, so we are balanced. Take a minute to try to come up with the chemical equation for the reaction I've represented here, and then we can check our answers and go through the balancing process together. So this tells us that etching occurs when hydrofluoric acid and hydrofluoric acid. Remember, since we see that term hydro, it means we are not dealing with a polyatomic. So hydrofluoric acid means I am looking at hydrogen as the cation, and fluoric comes from fluorine. And if we look back at our periodic table and how we labeled the columns, we can see that fluorine has a -1 charge. Hydrogen has a +1. So this means that the formula we're looking at is just HF, 1 hydrogen to 1 fluorine. This is saying that it reacts with, so we have a plus. Remember, we did say that all acids are aqueous, so even though it doesn't say it, we can put aqueous in parentheses to represent the state. Silicon dioxide. We know silicon is Si, and di is referring to the number of oxygen in this formula, so we have SiO2 as the prefix di indicates. So this is SiO2. So we can use contextual clues here, or the words around what we're looking at to determine what state this is in. So this is silicon dioxide, and it says it's in glass. So we find glass in solid form. To form gaseous silicon tetrafluoride, so again, we're looking at silicon. This time we're looking at fluorine, and as indicated by the prefix tetra, that becomes 4. So that to form means we're moving on to the products. Silicon tetrafluoride is SiF4, and we're told that this is gaseous. That's a G, gaseous. And liquid water, H2O, liquid. Now, we draw a line where the arrow is to separate the reactants from the products. List the elements that appear on both sides. We have H, F, Si, and O, and then count the number that appear on each side. We have 1 hydrogen on the left, we have 2 on the right, we have 1 fluorine on the left, 4 fluorine on the right, 1 silicon on the left, 1 silicon on the right, 2 oxygen on the left, and 1 oxygen on the right. So you can see here that pretty much the only thing that's balanced is the silicon, but that can possibly change because we're going to have to go through the process of balancing out everything else. So there's a number of places we can start from here. But the way I would approach this is to start with the highest number. If we start with a lower number, that could potentially mean that we're just continually going back and forth until we reach that higher number anyway. So we'll have better luck if we start with the number that has the largest number of atoms. So in this case, that's fluorine. We can see that there's 4 fluorine on the right, there's 1 fluorine on the left, which means I need to put a 4 for a coefficient in front. This changes the number of hydrogen from 1 to 4, and it changes the number of fluorine from 1 to 4. Now, this gets us pretty close. I don't want to mess with the fluorine on either side. I do want to change the number of hydrogen on the right side now, because I can see now that I have 4 on the left, I only have 2 on the right. So remember, coefficients multiply. So if I already had 2 and I multiply that by 2 more, that gives me a total of 4. Now for oxygen, that's the only place that oxygen exists on the right side. Since I had 1 in the formula and put a coefficient of 2 in front, this changes the number of oxygen from 1 to 2. And now we have the same number of each element on each side, so we are balanced. The last step in the process of correctly writing an equation to represent a reaction is to be able to identify the type of reaction that we have. And there are several different types of reactions. This can help us if we know in the statement what type of reaction we have. This can help us predict products. So 6 different types of reactions, and we'll go over examples of each. We have synthesis, decomposition, single replacement, double replacement, combustion, and oxidation reduction. We don't get into oxidation reduction reactions at this level, but if you go on to take AP, then we will discuss them in great detail in that next level. So in a synthesis reaction, if you've heard the word synthesis before, this is referring to things being made or two things coming together. So in a synthesis reaction, we are combining two reactants to make one product. So you might be given a clue, like in the synthesis reaction of hydrogen and oxygen, water is formed. And that will tell you you're only looking at two reactants and forming one product. In a decomposition reaction, we've already talked about this. Decomposition means one thing that's breaking down into multiple products. So if you see the word like we saw in one of those previous examples, if you see that something decomposes, that means you have one reactant. And that's important because that gives you a big hint about what this reaction is going to look like. One reactant breaking down into multiple products, and that can be one, two, or I'm sorry, two or three products. Single replacement means one thing is being replaced, or a better word for this is one thing is switching. So in this case, we can see that we have a copper element, and then we have a silver cation in this compound, and we can see that's what happens here is that they switch places. So when we say replacement, we're really meaning they're switching places, or we can kind of look at this as the copper is replacing the silver in this reaction. But you have to be careful here because you have to know how these things break apart. It's not always easy as just switching their places because as we can see here, the formula actually changes to represent the type of copper that we have. Copper, remember, is a transition metal, which means it can have a +1 or +2 charge. And we don't really know unless we're given that hint in the statement. So I would not expect you to be able to come up with this product on your own unless I tell you that copper 2 nitrate is what's formed as a product in this reaction. Otherwise, what a lot of people tend to do is literally just replace silver with copper and write the formula the same way. But remember, these are two different formulas. The one on top is copper 2, as indicated by the 2 outside of nitrate. The one on the bottom is copper 1, as indicated by the 1 outside of the nitrate. But according to this equation, it's the copper 2 ion that we're looking for. So single replacement is when we just have one thing that's switching places. In double replacement, we have two new compounds that are being formed. So we still see the same thing. We still see the cations trading places, but we see that two new compounds are being formed as a result. So it helps if we can break these down into their individual ions, and we see that that's H plus and Cl minus, and we know that this is Na plus and S2 minus. And then if we just switch the cations, we can see that's exactly what's happened on the other side. Now we see that sodium is paired with chlorine, and we see on the other side that our hydrogen cation is paired with the sulfur anion. And it's good to separate these so we can see what carries the charge with it. So we don't want to carry the 2 with the sodium because the 2 is not attached to the sodium. The 2 is actually attached to the sulfur. So breaking this apart as ions helps you see then how those elements carry their charges with them to the other side of the equation. In a combustion reaction, we have a fuel that combines with oxygen to form carbon dioxide and water. So this is the fuel we're talking about, and a fuel is most often a hydrocarbon. That's what we're referring to, is anything that has both carbon and hydrogen together. So we can see that this is combined with oxygen, and as a result, we get carbon dioxide and water. So like I said, if you're told you have a combustion reaction, you know that that automatically means that you're adding oxygen. You also may see the term burning in air. Burning in air means we add oxygen. So if you see combustion, if you see burns in air, both of those things are referring to the fact that oxygen is one of our reactants. And then from there, we can predict that we're going to end up with carbon dioxide and liquid water. Take a minute, practice these problems, see if you can identify what types of reactions we have here, and then we'll come back together to discuss the answer. So you can see in number one, we have one reactant breaking down into multiple products. This is a decomposition reaction. One thing decomposing into two other things. In number two, you can see oxygen is a reactant, and oxygen, furthermore, is mixed with a hydrocarbon. This is a combustion reaction. We have a hydrocarbon mixed with oxygen, forming carbon dioxide and water, combustion. In the next one, we see that just one thing has switched places with something else or replaced something else. So this is an example of a single replacement reaction. In the next one, we have two reactants coming together to form a product. This is a synthesis reaction. You might also see the word combination, same meaning, two things combining to form something else. And in the last one, we can see that what we really have happening here is one cation is switching places with the other, or one cation is replacing the other one, and we end up with two new compounds. So we end up with a double replacement reaction in this case.